Sorry, storage ran out. Alright, so now continuing from here, we sum. What in the world? This is not supposed to have a negative sign or a 4. I'm just stupid. Or 3. Okay. Anyway, now moving from here, we sum these together. Then this gives us negative AR to the 4th over 3 epsilon naught R squared in the R hat direction. And then finally for D, it asks, what do we expect to happen inside as the power of R increases for the polarization? So we noticed here in the beginning we had polarization goes as R, and then we ended up with a electric field that goes as R. Here we have a polarization that goes as R squared, and an electric field that goes as R squared. So I expect that as R increases, the electric field is going to increase by the same amount. And then it says to check this with P equals A R to the 4th in the R hat direction. So for this polarization right here, once again, D equals 0, and then 0 equals epsilon naught E plus P. Doing some ranging, epsilon naught E equals negative A R to the 4th in the R hat, and E equals negative A R to the 4th over epsilon naught in the R hat direction. So it just turns out whatever the polarization is in these cases, it's just going to be the polarization over epsilon naught. So that's problem 4.10. Now, next Pencast problem, we have problem 5, which gives us a hollow insulating rod that has inner radius A and outer radius B, and has a polarization inside of C over R squared. And then part A, we're given that the vacuum is in for R less than A and R greater than B. So all the polarization is in this region right here. And free space is just 0. So what does that tell you about P in those regions? As I just said, P is 0 in those regions. Then it asks to find the bound charges on both surfaces. So sigma bound at A, P hat dotted with N hat. Once again, N hat and P are in the same direction, the R hat direction. So, except here, N hat is going inward, here it's going outward. So it's actually they're opposing. So it's negative C over R squared evaluated at A, so C over A squared. And then at B, now P and N hat are in the same direction. So evaluated at that value of R, we get C over B squared. Rho B, negative del dot P. Okay, negative del dot P. So for cylindrical, that's negative 1 over R partial with respect to R times P in the R hat direction, which is the C over R squared. And there's no theta or phi hat direction, so that's all we worry about. And that gives us C over R cubed. Then part B, whereas use these bound charges along with Gauss's law to find the electric field everywhere in space. So we know that rho free equals 0. So we have for r less than a, the integral of E dot dA equals Q enclosed over epsilon naught, but Q enclosed is 0 since there's no free charge. And since E and dA, by symmetry, E and dA are in the same direction, we have E A equals 0, A does not equal 0, so E for R less than A equals 0. So now we go to R greater than A less than B. So integral E dot dA equals E integral of dA, which equals E times 2 pi RL, which is equal to Q enclosed over epsilon naught. E equals Q enclosed over 2 pi RL in the R hat direction. So now we need to find Q enclosed. It's just going to be sigma of BA, which is sigma right here, times the area plus the integral of rho bound dV. From this part, we have negative c over a squared times 2 pi AL, which is negative 2 pi CL over A. And this right here is the integral from 0 to 2 pi, integral from 0 to L, integral from A to R, C to the R to the negative third, and then times the area element, or volume element. And when we take the integral of this, we find that this is minus 2 pi CL over R, plus 2 pi CL over A. These cancel. So Q enclosed is just negative 2 pi CL over R. Plugging that in for Q enclosed up here, we find E for A, R less greater than A less than B is negative C over epsilon naught R squared in the R hat direction. And lastly, for R greater than B, we have the same expression right here, but now we just need to find what Q enclosed is. So for Q enclosed, we go back to, these parts are still going to cancel. So we're going to have the negative 2 pi CL, and now R is evaluated at B instead of R. And that comes B. And then we have sigma bound. Right? Yeah, sigma bound B times A, so it's negative 2 pi CL over B, and it turns out this part right here is also 2 pi CL over B, so these are opposites. That gives us 0. Since Q encloses 0 for this region, E is 0 as well. And then part C, we're asked to do all this over again, but in a much simpler way. So we have to use equation 4.23 to find D everywhere in space. So we know that there is no free charge since rho free is 0. So that's 0. So this equation is integral of D dot dA equals Q free enclosed, which is 0. So D integral of dA equals 0, or by symmetry, or D equals 0, since integral of dA or A is not 0. Part D, we're now asked again to find the electric field everywhere. So for R less than A, we have the displacement, which is 0, is equal to epsilon naught E plus P. But this is free space, so P is 0. So we have epsilon naught E equals 0. Epsilon naught's not 0, so thus E must equal 0. For R greater than A less than B, 0 equals epsilon naught E plus the polarization, which is C over R squared in the R hat direction. After rearranging, you have E equals negative C over epsilon naught R squared in the R hat direction. And lastly, R greater than B, 0 equals epsilon naught E plus polarization. Again, once again, we're in free space, so polarization is 0. And since epsilon naught cannot be 0, E again equals 0. And these right here are the exact same thing we found up here, just much faster, which just shows us the power of this displacement. And that is the end for Pencast.